Okay, so just to record this, solid sphere, uniform charge density rho, the radius of the sphere is r, and the question is find the electric field inside the sphere, and then r greater than r, which is outside the sphere. Outside the sphere is going to behave like a point charge in the center. So we will do the r greater than r first. Just get that over with. It's going to be like a point charge. So it's going to be, the electric field is going to be Q over 4 pi epsilon naught times 1 over r squared and then r hat, right? That's the electric field. But Q is rho times the volume. Okay? So that's the total charge of this inside the sphere. So it's going to be the charge density times the volume. V here is volume, not voltage, right? I know we were discussing potential difference. Now volume. 4 pi epsilon naught 1 over r squared r hat. So you get rho, and then 4 thirds pi r cubed. I'm sorry, 4 thirds pi capital R cubed, and then 4 pi epsilon naught times 1 over r squared r hat. Cancel the 4 pi, and you end up with rho r cubed over 3 epsilon naught times 1 over r squared r hat. Yes? That's the electric field. So basically just k q over r squared, and then q is the charge enclosed in here. Okay? When you're outside, the charge is just within the sphere, nothing beyond. There is no charge beyond. So now inside the sphere, that's the one I really care about because the next problem that I'm going to give you. Inside the sphere, you draw a Gaussian surface, right? Here is your Gaussian surface of radius little r, and ask, and then apply Gauss's law. For r less than r, you would have E dot dA closed surface equals to Q enclosed over epsilon naught, right? Okay. E dot dr, E dot dA, the electric field points radially outward. dA points in what direction? Also radially outward, so they're parallel. So E dot dA becomes EdA. E is the same over the entire surface. You pull it out, so it just becomes EA. And what is A? 4 pi little r squared. It's the surface area of the Gaussian surface. Okay. Epsilon naught. Q enclosed would be the charge density times the volume. Is it the volume of the whole sphere? No. I'm enclosing only this portion. Right? Only this portion has the charge is within my Gaussian surface. So I got 4 thirds pi what? Yeah, it becomes 4 thirds pi little r squared.
So that's the
Q. Oh, Q. Yeah, it's a volume. Yeah, thank you. Now my 4 pi, and this one, all of them cancel, and we get what? E rho over 3 epsilon naught r, right? And then since it's radially outward, it's going to be r hat. And I would prefer to actually write this one. I'm going to write it this way. What is r times r hat? The vector r. Yeah, so it's going to be this. E will be rho over 3 epsilon naught times the vector r. Okay? So this is inside the sphere.
You want it like that on the test or just either way?
For what I'm going to do next, this is more convenient. Yeah, but either way is fine. Yeah. so this is inside the sphere, right? Where is R measured from? The center of the sphere. Good. Okay. I'm asking these questions for a reason. Because the reason is this next problem. It's not well. You tell me. Here is a sphere. Okay, ready? This next example is looks like this. The same solid sphere we had earlier, right? Again, solid sphere. Okay, charge density rho. Charge density rho. Uniform charge density, constant. The radius is still r. Okay, everything's the same. So rho is constant, and radius is r. So okay, and we know what's the field inside this sphere, right? It's this. It's exactly that. Okay. Here's what we're going to do to it. So here's the x-axis. I'm going to just horizontal here, like ice cream.
No.
So you scoop out this. So scoop out, so whatever your favorite thing is, so cut it out. So we're going to scoop it out, so meaning this. So what's inside here then? A cavity, yeah. So here, so at the edge basically, it's basically cut up, right? So this one will have radius r over 2, right? That's the cavity. That's r over 2. Because from here to here it's r, and we scooped out the whole sphere. Yeah.
Is it like a hemisphere scoop out, or can we say that we really got
The whole bulk, whole sphere.
And it's within the our solid sphere,
Yeah.
so we can't. If there was like an actual 3D object, we wouldn't be able to see our cavity, or can we somehow see?
There would be a cavity. Yeah.
That we could see from the apple.
Well, at this point, there would be one little hole here.
One little. Okay,
Yeah,
so it's
at that
just
one
perfectly
point, okay.
tangent.
Yeah, yeah. You can't really see it because that hole is like 0, basically.
I hear you.
Okay. Okay. Yes.
So is the surface of the sphere gonna be open or still closed? The surface of the sphere.
So if you're concerned about Gauss's law, you're saying open surface. So Gauss's law is always a closed surface. We don't. It has nothing to do with this one being open and closed.
Oh.
Yeah. So here's the question. Okay. So again, we agree that what's the total charge inside here? What's the charge here? Not the field. The charge here. Yeah. We scooped out something, right? So it's basically vacuum. So there is nothing, so it's 0, right? So the main idea is the charge here is 0. The charge here, we got rho, right? The charge density here is rho. So what's the electric field inside this cavity here? What's the electric field inside this cavity? And it's not 0.
Oh.
It will not be 0. It will actually, and you can tell, right? Because take a little DQ here, it will contribute an electric field that way, another DQ will contribute it. So you end up with a field.
If it were in the center, it'd be 0. But
Yeah.
but it's not in the center.
It's not in the center, it's off center.
But if you made a Gaussian surface within that cavity, it would be close to 0 charge.
Including 0 charge doesn't mean 0 field.
But it's here close to 0. What if the other side of the interval?
Yeah, here's the charge Q. Here's the surface. Remember this one? E dot dA is going to be 0, but E is not 0 on any of the points. Yeah. So, so the question is, what's the electric field inside this cavity? So, I want to make sure, before we even answer this, I want to make sure that we understand what the problem is asking. That's what I want. Okay? So before we worry about all the details, is the problem statement, okay?
I don't understand why there's no charge inside of the cavity.
Because it's a cavity, it's empty. You're
Oh.
asking, I think you're thinking field.
Oh yeah.
Right?
I got the point.
The field is not 0. Yeah, but the cavity is, yeah.
through stage, we want to find the electrical field at the center of the cavity.
No, anywhere inside the cavity.
Anywhere in the
Yeah.
cavity. Alright.
Yeah. So I might be implying the electric, it's gonna be a simple thing. It's not gonna be zero though. It's gonna be some number, some value. It could be some symbols, but it's going to be just one set value, okay? So how are we going to solve this?
Max's law?
Huh?
Use Gauss's law?
We can use Gauss's law. The problem as it stands, there is no symmetry. We don't have spherical symmetry. Yeah, that's the problem, right? It has a cavity now, so there's not enough symmetry that we can apply Gauss's law.
Would you subtract the volume of the cavity from the volume of the whole thing?
That would be basically the idea.
You'd split it into
Oh,
two
yeah.
integrals.
No integrals at all. Yeah. So here's what we're going to do. Okay. So we're going to say, let's solve another problem that's equivalent to this problem. So here's the problem that you can think of. Okay. So here's the problem that we can think of. So this problem is equivalent to this. Okay. Here's a problem that's equivalent to it. Take a solid sphere. Don't take anything out of it. So you have your solid sphere, with radius r, and charge density rho. Okay? Plus, we're going to have a smaller sphere of radius r over 2, but it will have charge density. If I put minus rho, yeah, if I put this minus rho here, like superimpose it on top of it, what would the total charge be here? Yeah. So this product equivalent to that. So do I know the field of a solid sphere?
Yeah.
Yes. Do I know the field of another solid sphere? Yes. I just have to add them.
Wow.
Yeah. That transferred the tough product to a much easier. Yeah.
I think this one is charge distribution of the values of cavity equal out is equal to the negative.
So when you put this one in, add the pressure on top of this, what was the total charge? Right?
Wait.
Zero. I will. Yeah. Let me start with dim and then I go this one. Yeah.
Aren't we trying to find the fields inside the cavity?
Where
Yes.
is the
What,
row?
wouldn't this
It's the
solve
negative.
for
Why
the
don't we
fields
just
outside of the
put-
cavity in the bigger sphere?
Hang on.
But it's not
And then. Yeah.
Why did we say that that's the smaller
It's
sphere?
the same way.
We were saying it's
The
a
one that
cavity.
starts with right hand.
Yeah.
Because it has nothing inside it, right? So
Yeah.
say-
So the most important part about the cavity is the net charge is zero, right? Not the fact that it's vacuum. Is that the net charge is zero. So this one, when I add it on top of it, yes, it's not vacuum, but what's the net charge? Zero. So as far as fields are concerned, they care about the charge, not about it having mass or not mass. Yeah.
So because we're not using Gauss's law for this, it doesn't necessarily matter that it's a sphere or a
How long
hollow.
is it negatively?
As far as charge, like electricity is concerned, if the net charge is zero, whether you have a cavity or you have mass in there, as long as it's neutral or zero, then it is fine. Yeah.
We know how to find the electric field of a sphere, but for the smaller one, it would be we know it as a radius from the very center.
Okay, yeah, that's
That's
the
all
next,
good.
yeah, so, you're ahead. Yes,
Can you explain again why the charge instead of the cavity is negative rho? Like why is the charge negative rho for the cavity?
it's not, the charge is zero, right?
Yeah.
Yeah.
I'm saying, if this one is rho, all of it is rho, and I add to it just this part here, and I add the negative rho right on top of the rho, what would the total be?
Well then zero, right?
Yeah,
Oh, I see.
that's why I'm saying it's this plus this is equivalent to that.
Oh.
Wait.
Yes, so, yes,
Like, can a density be negative?
yes, of course it could. You can have negative charge, right?
Oh.
Yeah. Okay, let's get to the problem because I have about 9 minutes. Okay, so and then you can reflect on it and then maybe ask further questions later on. Okay, so I want to just demonstrate how we can do this. Okay, so here it is. So I'm going to choose some random point. So choose a point inside here. Here is a point. Let's draw it with red. Okay, that's the point. Let's figure out the electric field due to the solid sphere. Right? So I'm assuming now I have a solid sphere of rho, and then another solid sphere of negative rho. That's what I'm saying. So what would be, so here is R. What's the electric field due to a solid sphere? Let's call it E1. This. Okay. What's the electric field due to a, let's use red for this one. Here is this other sphere, this sphere of radius r/2. Let me call this here r prime, right? They cannot have the same r. This one, the origin is shifted. This is r prime. So what would the electric field E2 be for this? It's still a solid sphere, but the density is negative rho. So what can I say? Minus rho over what? 3 epsilon naught. Yes. R prime. Yes. It's going to be r prime because r is measured from the center, right? It's the distance from the center. The center of this one to this point is r prime. So now the total field is going to be what? The field due to the solid sphere plus the E2. Yes, let me finish it and then I'll get back to that. So here, when I add them, what do I get? Not really. R minus r prime is not 0. So you get this. Rho over 3 epsilon naught times r minus r prime, right? R minus r prime. And then, what's this vector this way? From here to the center. Yeah, it's what? R/2, what? I hat, right? I mean, here's I hat. Yeah, so what do you do? R/2 I hat plus r prime is equal to what? This vector plus this vector, what do they give you? Vector r. So vector r minus vector r prime is equal to r/2 I hat, right? So this is r/2 I hat. Yeah, give me 1 second. Oh, let me just write it down. 6, 7, 9. I hat. And get to your question and then to your question. Yes? Oh, I said this vector plus this vector, they're equal to this vector.
So that you can put purple vector in terms of the r prime vector.
So when I'm looking for the difference here. So this vector is r/2 I hat, right? R/2 I hat. Plus this vector is r prime. Let's move r prime to the other side. Sammy, I think I said I postponed your question and now I'm ready to. Okay, it answered itself. That's good. Yeah. So that's the answer. So what do you notice about it? Is it changing?
No.
No, it's constant. Yeah, it's a constant. So the electric field in the cavity is just pointing to the right, and it has one magnitude, and that magnitude is this.
No matter what, R minus R minus
Yeah. You will notice, why did I answer this? In one of the previous tests, someone looked at it, and I forget that it was one of them that I posted. You had one of these things. Yeah. Yes?
I know that one. I think I was just doing it. I want to say I used
Huh?
I wanna say that I use Gauss's law for whatever solution. I don't know, I haven't checked the solution.
Yeah, you will, to use Gauss's law for the problem as a whole, you can, because there is not enough symmetry. But Gauss's law for one sphere can be used, and Gauss's law for this other sphere can be used, and then the combination, I just added there 2 fields. Okay? So we're gonna continue the review later. So try it, think about it, and then maybe ask some questions. At least